OCR Chemistry A 5.3.1 Ligand substitutions and precipitation reactions. Using Chemistry Explained means participating by writing notes and completing the tasks with a pen on paper or on a tablet. Pause and replay the slides at the pace that suits you. Most importantly, when prompted, pause the lesson, thinking a problem through, taking your time, completing the task before continuing and correcting your work. Our overview, we're going to look at ligand substitutions and precipitation reactions through the chemistry of particular aqueous ions: copper 2, chromium 3, iron 2 and 3, and manganese 2. Copper salts such as copper 2 sulfate dissociate in water to form aqueous ions. Up to the study of transition metals, you may have written that dissociation as a reaction equation as shown. Copper sulfate dissociates to form the aqueous copper 2 plus ion and the aqueous sulfate ion. However, it is more accurate to represent the copper 2 plus ion as a complexed ion, the hexa-aqua copper 2 ion of this formula, with which I hope you are familiar. If you are not, you need to move back to some of the earlier lessons on the transition metals. This, of course, is a complex ion. We have a central transition metal ion, the copper 2 plus, forming coordinate bonds to 6 ligands, 6 water molecule ligands. So working with copper 2 plus ions, let's look at their ligand substitutions. So the first example is with excess ammonia. So here is our aqueous copper 2 plus ion, our aqua complex. Please note it is pale blue in colour. You are expected to recall that. It reacts with 4 ammonia in a reacting ratio 1:4. Now, bearing in mind that we're talking about ligand substitutions, and I've given you the correct balancing for the left-hand side, pause and propose the products of this ligand substitution. Come back when you've written down your answer. So I'm about to reveal. 4 ammonias substitute for 4 water molecules. So 4 water molecules are removed from the complex ion and replaced with 4 ammonias. How do we know it's 4 ammonias? Very simple. The specification, the OCR Chemistry A specification, states that the formula of the complex formed in this situation is as I've written it. So it's straight factual recall. You're also expected to know that this will form a dark blue solution. We know it will be soluble because the complex ion is charged. A ligand substitution also takes place in the presence of excess hydrochloric acid. So let's write down the left-hand side for that ligand substitution. Again, we've got the aqua complex, the copper 2 aqua complex. We know that it's pale blue. We know it's soluble because it's got a charge. I am telling you that 4 chloride ions are used on the left-hand side. It is a reacting ratio of 1:4 between the copper ion, copper complex, and the chloride ions. Using that information, pause, propose the products. Write them down, come back to check against mine in a moment or two. Okay, so I'm going to reveal. Now, this is slightly unusual in that we have a change of coordination number. So I wouldn't be surprised if you didn't get that right. Instead of having a coordination number of 6, copper changes to a coordination number of 4 with the much larger chloride ion. So we have CuCl4 2-, and all 6 waters leave the complex ion. You are also expected, that again is provided for us by the exam board as a fact. We are also expected to recall that the colour of the solution formed, and it's a solution, notice the complex ion is charged, so it will be soluble in water. The colour of the solution formed is a pale yellow. This is a slightly, well, it's an unusual ligand substitution in that there is a change in coordination number. The coordination number for the copper in the aqua complex is 6. The coordination number for the copper in the chloro complex is 4. And of course that will also change the geometry. Pause and state the shape of the aqua complex and the shape around the copper in the chloro complex. Come back when you have thought it through. Okay, so the aqua complex, we've got 6 ligands, so that will be octahedral around the copper. Here we've got 4 ligands, so that would be tetrahedral around the complex. Refer to the earlier lesson on ligands if you are not clear on that. So let's look at some precipitations for aqueous copper 2 ions with drops of dilute sodium hydroxide. Please note I've highlighted drops to contrast with excess. So with drops of dilute sodium hydroxide solution, one gets a precipitate. Here is the aqua complex. So 1:2 reacting ratio with hydroxide ions. Bearing that in mind, pause and propose the products on the right-hand side. Come back when you are ready to check against my answer. So I'm about to reveal. We get a blue or pale blue precipitate. The hydroxide ions each acquire a hydrogen, a proton, from the complex to form 2 moles of water. So 2 moles of hydroxide ions become 2 moles of water. What does that leave within the complex? Well, we've still got copper, obviously. We've got 4 water molecules, but 2 water molecules have each lost 1 hydrogen. So we're left with 2 hydroxide ions. So we've got copper, 4 waters, and 2 hydroxides. Overall, 2+, and each hydroxide is 1-. Overall, the complex has no electrical charge, and therefore it is insoluble. Please note there is no further reaction with excess sodium hydroxide. There's only a reaction with drops. There is no further reaction with excess sodium hydroxide. So aqueous copper 2 also undergoes precipitations with drops of dilute ammonia solution. So here is the reactant side of this precipitation, a 1:2 ratio between the complex ion and ammonia. Pause and propose the products. Come back when you are ready to check against mine. So I'm about to reveal. The ammonia molecule accepts a proton to form the ammonium ion. 2 ammonias form 2 ammoniums. So what was 6 water molecules has become 4 water molecules. 2 of the water molecules have each lost the proton to form hydroxides. So we're copper, 4 waters, and 2 hydroxides. Overall, electrically neutral, therefore insoluble. It's a pale blue precipitate, as we can see in my little diagram here. Now, what happens if you keep adding ammonia? Well, in excess ammonia, the precipitate will dissolve. Here's the precipitate. It's a 1:4 reacting ratio with ammonia. Propose the product side. Pause, come back when you are ready. You've thought it through. Come back to check against mine. I'm about to reveal. So, 4 ammonias substitute into the complex. So we've got ligand substitution, 4 ammonias substitute in. 2 waters are lost and 2 hydroxides are lost. So we're left with copper, 4 ammonias and 2 waters. How do we know that that's the correct formula? The exam board have told us that in the specification. So this is the formula of the complex formed. You'll notice it's got a charge. That explains why we get a dark blue solution. Ionic property is solubility in water. So the charged complex ion will be soluble in water. So we can say that the precipitate is soluble in excess ammonia. Some aqueous chromium 3 chemistry. In aqueous solution, the chromium 3 ion is better represented, of course, by the aqua complex CrH2O6 3+. As pure, this forms a violet solution, but with impurities it may appear as green. Ligand substitution occurs in excess ammonia to form a purple solution. So here is our pale violet aqua complex, chromium 3 aqua complex. I'm letting you know that the reacting ratio is 1:6. It's a ligand substitution. Put that all together to propose the products. Come back to check against my answer when you're ready. So I'm about to reveal. Well, 6 ammonias substitute into the complex and 6 waters come out, and that leaves us with a 3+ charge on the complex ion, so no change in that respect. We have a stronger purple colour, and you are expected to know the colour of this particular complex ion, which is stated in the specification, and you're expected to know its colour. So aqueous chromium 3 also undergo precipitation reactions with drops of dilute sodium hydroxide solution. So here is our aqua complex. It's a 1:3 reacting ratio with the hydroxide ion. We need to form a precipitate. Put those ideas together and deduce the products on the right hand side. Come back to check when you are ready. So I'm about to reveal. So 3 hydroxides each accept a proton to form 3 moles of water. That leaves within the complex 3 water molecules unchanged, and 3 water molecules have lost a proton to form 3 hydroxides. Overall, it is electrically neutral and therefore insoluble. So because we're forming a grey-green precipitate, and you are expected to know and recall the colour of the chromium 3 hydroxide precipitate, so although we are writing the complex, it could just be known as the chromium 3 hydroxide. That's true for the other hydroxides that we've encountered. We know it's insoluble because we formed a precipitate. That means we must have a 3+, we must have 3 hydroxides within the complex so that the electrical charge is neutral. Exceptionally, chromium 3 hydroxide will dissolve in excess sodium hydroxide solution. So here is our precipitate. It's a 1:3 reacting ratio. That's information that I'm giving you. So it's 1:3. Propose the products. So I'm going to reveal. 3 waters are replaced by 3 more hydroxide ions. So we now have chromium 3+, 6 hydroxides at 1-, so the overall charge is 1-. And of course, because it's charged, it will be soluble, dark green solution, and you are expected to recall that. So we get a grey-green precipitate with drops, and electrically neutral complex is formed. In excess sodium hydroxide, chromium 3 hydroxide will dissolve to form a dark green solution. Precipitations will also occur for aqueous chromium 3 with drops of dilute ammonia. So here is our left-hand side. Again, we've got a 1:3 reacting ratio. Pause the lesson. Propose the products for this reaction equation. Okay, so I'm going to reveal. Again, each ammonia has accepted a proton to form the ammonium ion. There's 3 ammonias to form 3 ammonium ions. So 3 water molecules of the 6 have lost the proton, 1 each. So we're left with 3 water molecules and 3 hydroxide ions within the complex. Therefore, it's electrically neutral, 3+ and 3 ions at 1-. So it is insoluble. It is also a grey-green precipitate, as we saw on the previous slide. Chromium 3 hydroxide will dissolve in excess ammonia solution. And again, I'm going to ask you to complete the right-hand side. It's a 1:6 reacting ratio. Use that to deduce the products. Come back when you're ready. Okay, so to reveal, so 6 ammonias substitute into the complex, removing or replacing 3 waters and 3 hydroxides. So we're returning to a charged complex, and therefore it is soluble. It forms a solution. You are expected to recall that the solution is dark green. Aqueous iron 2 and iron 3 chemistry. Iron 2 salts dissociate in aqueous solution. Of course, we get the aqua complex FeH2O6 2+, which is, you are expected to recall, is pale green. Precipitation reactions occur with drops of sodium hydroxide. Here we can see the precipitate, a dark green precipitate, starting with the complex. It's a 1:2 reacting ratio. Deduce the product side. Pause, come back when you're ready. Okay, so to reveal, 2 moles of water are formed from the 2 hydroxides. 4 waters remain within the complex. 2 waters have each lost a proton to form 2 hydroxides. So we've got Fe2 plus and 2 hydroxides, so electrically neutral, it is insoluble. Similarly, precipitations occur with drops of dilute ammonia. Again, it's a 1 to 2 reacting ratio. Pause, write down the products. Okay, to reveal, again, I'm hoping you're seeing a pattern. Dark green precipitate, instead of 2 waters, we get 2 ammonium ions. So each ammonia has accepted a proton, 2 water molecules have lost the proton to form 2 hydroxide ions, 4 waters remain. Electrically neutral, therefore insoluble. There is no further reaction with either excess sodium hydroxide or excess ammonia. So iron 3 salts dissociate in a similar way to iron 2 to form the complex iron-iron FeH2O6 3+, and this forms a pale yellow solution. Precipitations occur with drops of sodium hydroxide. It's a 1 to 3 reacting ratio to form orange-brown precipitate. Complete the reaction equation. Come back to check when you are ready. Okay, so 3 hydroxides become 3 waters. We have 3 waters remaining within the complex, but 3 waters have each lost a proton to form hydroxides in the same way as previous slides. Electrically neutral, it is insoluble. We can similarly form a precipitate with drops of dilute ammonia. Complete the reaction equation. Come back to check when you are ready. Again, an orange-brown precipitate is formed. Same formula, same complex iron formula as with sodium hydroxide. Instead of forming 3 moles of water, we have 3 moles of ammonium ions. Again, in excess, there is no further reaction in excess. Oxygen is transported around the body in the blood, the red blood cells, by the globular polypeptide hemoglobin, which contains 4 heme groups, each with a central iron 2+ ion. Now here's an outline of a heme group. We've got iron coordinated to 5 nitrogen atoms, which are themselves then part of larger molecular structures. This is deoxyhemoglobin. If we look at the addition of oxygen, or the binding of oxygen to the iron, we can see that the coordination number 6 is achieved by the iron 2 ion, and we have a binding between iron and O2, molecular oxygen. That binding, or the oxygen bonds, reversibly. So in the lungs, deoxyhemoglobin picks up oxygen to become oxyhemoglobin. Oxyhemoglobin is transported to the cell where oxygen is released and deoxyhemoglobin is reformed. Oxygen is obviously required for respiration. Carbon monoxide is highly toxic. The chemistry behind this is that it can also bind to the iron 2+ ion in hemoglobin via a ligand substitution. So if we look at our oxyhemoglobin coming into contact with carbon monoxide, molecular oxygen here is acting as a ligand, So this is a dative covalent bond, a lone pair from oxygen, forming the dative covalent bond or coordinate bond with the central Fe2+ ion. We can exchange or substitute the carbon monoxide and remove from the complex the oxygen. So this is ligand substitution. What forms is carboxyhemoglobin. Now the binding of the carbon monoxide is irreversible. So carbon monoxide poisoning reduces the availability of hemoglobin to carry oxygen, preventing its transport and leading to death. Aqueous manganese 2 chemistry. Manganese 2 salts dissociate in the expected way and form the complex ion manganese or hexaaqua manganese 2. You are expected to know both that formula, not necessarily the name, the formula, and its colour in solution, which is pale pink. Now, manganese 2 chemistry shows precipitation reactions with drops of dilute sodium hydroxide. Again, it's a 1:2 ratio. We form in that precipitation a pale brown precipitate, an insoluble pale brown precipitate. Pause, complete the reaction equation. Come back to check. Okay, so here is the reaction equation. Again, 2 hydroxides form 2 waters. 4 waters remain within the complex. 2 hydroxides remain within the complex. Manganese is 2+, 2 hydroxides at 1- means we're electrically neutral. It's insoluble, a pale brown precipitate. You have to recall the colour of the precipitate. A second precipitation reaction occurs with drops of dilute ammonia. Pause and complete that reaction equation. I'm about to reveal. Again, 2 ammoniums forming from 2 ammonias, 4 waters remaining. 2 waters have become 2 hydroxides by losing a proton, 1 each. Electrically neutral, it's insoluble. There is no further reaction with either excess sodium hydroxide or ammonia. So you can find some suitable practice questions if you have access to the OCR endorsed textbook on page 417. Summary questions 1, 2 and 3, you'll find the answers on page 582, or you can use other textbooks which will also have suitable questions.